So we were discussing noise margin last time. Right? And what was the idea here? We basically had the voltage transfer characteristics VTC, V out versus V in for an inverter like this. V in, V out. Okay. So the VTC is like this. And we said that the point at which the slope becomes -1 is of significance because before that, right, or outside that, the signal gets attenuated or noise gets attenuated. Within that region, the noise gets amplified, and therefore the region of importance is between the points at which the slope is -1. Okay, that's why -1 is a magic number here. Okay, so we basically said that this was VIL, this was VIH, right? The corresponding y-axis coordinates were defined to be VOL, and this was defined to be VOH. Okay, so the idea of noise margin is if I have one inverter driving another inverter like this, and I have noise fluctuating here, right? Then how does it go and how does it affect, if I have noise on each of these nodes, then how does the signal propagation get affected was the question, right? So for example, if the input was VIL, then the output of the first inverter, which is I1, and this is I2, output of the first inverter I1 would be VOH, right? But for VOH to get recognized as a logic high for inverter 2, VOH has to be greater than VIH, right? So therefore the noise margin high is VOH minus VIH. Similarly, if you gave VIH here, then you would get VOL here. The output of the first inverter will give you VOL, and for VOL to get recognized as a logic low on inverter I2, VOL has to be less than VIL. Therefore, the noise margin low is VIL minus VOL. Why noise margin? Because I have that much of margin for the noise to actually cause a fluctuation and not cause a change in the output, right? That is the margin that I have, and that's why it is called noise margin. Okay, and of course, to derive this, we had to make some assumptions earlier. We said that we'll take this point where V in equal to V out, right? This is V out equal to V in, and this point we would call it VM comma VM. That is, both input and output are the trip point VM. Okay, and we said that we will just extrapolate this slope, right? And then whatever intersects here, this is what we called VIL, and this point we called as VIH, right? This is what we did earlier. So last class we stopped at the point when we started discussing long channel inverter. Suppose we had a long channel device instead of a short channel device, then what would happen to this assumption? Is this model even valid, right? So let us go back to long channel inverters. Okay, which means that all short channel effects equal to 0. No channel length modulation, the velocity saturation voltage is very high, right? So therefore from linear it will only go into saturation, right? And all these things basically just vanish from our discussion. Okay. So now, if you remember the gain expression, right, equal to dV out by dV in at V in equal to V out equal to Vm was proportional to 1 over lambda n minus lambda p, right? And this is nothing but if lambda p equals minus lambda n, then this would be 1 over 2 lambda n, right? So because of very small value of lambda n, channel length modulation, this gain is very high, and we got some expressions from that, right? But of course, in a long channel inverter, what is lambda n? 0. So therefore, if I use this particular model to derive the VIL and VIH of the inverter, of a long channel inverter, what would happen is, because at this point, which is V in equal to V out, V out equal to V in, right? At this point, if I consider the gain, it is minus infinity, right? It's not plus infinity because the curve will fall, minus infinity, and therefore, if I do the same extrapolation, the curve will just extrapolate like this. Okay? And both VIH equal to VIL equal to Vm. They will both simply collapse to this point, though whatever I have shown here is not the VTC of a long channel inverter. This is the model that we used where we extrapolated the slope at V in equal to V out equal to Vm and pulled that line all the way up. That is the blue line. The actual VTC is what is shown in black here. It will come like this. At this point, it will be minus infinity, and then again it will deviate like this. So clearly this model that we used earlier works only for short channel device inverters, where lambda n and lambda p are non-zero, right? So now the question is, how do I derive an expression for VIL and VIH for a long channel inverter, right? So it turns out that the model was used in the first place because the expressions, current expressions for short channel inverters was very complicated, and therefore actually solving for this point when the slope is actually -1 on both sides was very hard, because you had velocity saturation, then you had channel length modulation, you had so many things, right? There's so many dependence on V in and V out. So solving for this point where dV out by dV in is -1 was very hard in a short channel inverter. Therefore, we use the approximation and the model, and that is a reasonable model, right? Now it turns out here that you don't have to actually use that model at all. You can derive everything from first principles, right? This is VIL, VIH, and this is VOH, and this is VOL, right? So at point 1, and this is point 2, dV out by dV in equal to -1. That's the definition for the noise margin, right? So in region 1, in which mode of operation is the NMOS, which mode of operation is the PMOS? Yeah? Okay, I need to, this is something you should really get used to. So maybe let's do it again so that you, this is V in, V out, this is WP by L, this is Wn by L, okay? In region 1, VOH is nearly VDD, very close to VDD, right? So let's again write these expressions, VGS, VDS, VDS for NMOS and PMOS. So VGS is what for the NMOS in terms of V in and V out? V in. What about VDS? V out. PMOS. V in minus VDD. And VDS? V out minus VDD. Okay. Now, VOH is nearly VDD. Right? Therefore, VDS for the NMOS is what? VDD. Nearly VDD. Right? V in is what? You can assume it's just above threshold somewhere. It's a very small value. So in which region of operation is it? VDS is greater than VGS minus VT, and therefore NMOS has to be in saturation. Okay. So in region 1, NMOS is in saturation, PMOS is in linear. Right? In region 2, NMOS is in linear, PMOS is in saturation. So we will now use these expressions in order to solve for the points VIL and VIH. Okay? What is IDSN? What is the saturation current? Remember, there is no velocity saturation now. It's a long channel inverter, so directly it is going to go into saturation. So what is IDSN? Half Kn prime Wn by L into V in minus Vtn whole squared. Right? This is in saturation current. What about IDSP? Yeah? Kp prime Wp by L into it's a linear current, right? So it is VDS into VGS minus VT minus VDS by 2. What is VDS? V0 minus VDD into V in minus VDD minus VTP minus V0 minus VDD by 2. Right? Now again we impose our good old condition. IDSN equals minus IDSP. Right? Two transistors in series, one current is going up, one current is going down, they have to be the same, and therefore IDSN equal to minus IDSP, which implies I can now write half into Kn prime Wn into Vin minus Vtn the whole squared equals minus Kp prime Wp by L into V0 minus VDD into Vin minus VDD minus VTP minus, I'll just leave this as it is, okay? I'm not going to simplify that VDD term for now. Right? So now what do? Differentiate both sides with respect to Vn. Differentiate with respect to Vn implies Kn prime Wn Vin minus Vtn equals minus Kp prime Wp into dV0 by dVin into Vin minus VTD minus VTP minus V0 minus VDD by 2 plus V0 minus VDD into 1 minus half dV0 by dVin. Right? Now let minus Kp prime Wp by Kn prime Wn equals R. right? Then I can say implies V in minus VTN equals R times dV out by dV in. What is dV out by dV in at that point? Minus 1, right? So therefore I can write this as minus 1. And what is V in at that point? VIL. At that point when the slope is minus 1, by definition it is VIL, right? Into VIL minus VDD minus VTP minus VOH minus VDD by 2, right? Correct? Plus V out minus VDD into 1 minus half of dV naught by d in will just become 3 by 2. So can you now simplify and get me an expression for VIL? Don't make any assumption, right? V out, by the way, is what? Actually, it is VOH. Yeah. Can you now simplify this expression and get me the expression for VIL? Are you getting this expression? Are you getting this expression? Right? Okay. Now what about VIH? You got to do the exact opposite, right? For VIH, PMOS is in which region? Saturation. NMOS is in linear. Okay, so can we write the expression for the currents? IDSP is KP prime half WP by L into VGS minus VTP the whole square, right? Which is nothing but V in minus VDD minus VTP whole square. And IDSN equals Kn prime Wn by L. What is VDS for the NMOS? Yeah? V naught. What about V in minus VTN minus V naught by 2? Right? Again, I go ahead and do the same thing. Equals minus IDSP, which implies Kn prime Wn into V naught into V in minus VTN minus V naught by 2 equals minus Kp prime Wp into V in minus VDD minus VTP the whole square. Again, differentiate with respect to V in. dV out by dV in equal to minus 1, right? Use this fact, implies Kn prime and minus Kp prime Wp by Kn prime Wn equals R, which implies I can write dV out by dV in into V in minus Vtn V0 by 2 plus V0 into 1 minus dV out by V in half. Right? Equals V in minus VDD minus VTP into R. So can you simplify this and tell me what you get for, of course here V in is nothing but VIH, V out is nothing but VOL. Can you get me the expressions? Equal to dV naught so this is what again this is 3 by 2 V naught plus 2 VOL plus R into VIH is VTN plus 2 VOL plus R into VDD plus VTP by. Do you get this? Yeah? Okay? Good. So I just derived the whole thing so that you get used to this kind of solving of these equations. Okay. So now let us compare the earlier expression that we also had, right? What was our VIL is VTN plus R into this. So can I copy this? Yeah. So VIL is this. So can you compare these two expressions and see what do you get here? I'm going to write this as VTN plus R into VDD plus VTP plus 2 VOL by 1 plus R. And this I'm going to write as VTN plus R into VDD plus VTP plus 2R, correct? VOH minus VDD by 1 plus R. So what is this region between VIL and VIH? How thin is this region? Right? Ideally, you would want it to be a zero thickness, zero indeterminate region. Right? You want the inverter characteristics to fall sharply like this, but inevitably there is a small region. So what is this delta V ILH, right? Which I'm going to call it as VIH minus VIL. Clearly you can see that this VTN and R into VDD plus VTP is sort of gone, right? So you basically have simply VIH minus VIL, right? So 2 VOL minus 2R into VOH minus VDD by 1 plus R. Right? So I can write this as 2 into VOL minus R into VOH plus 2R into VDD by 1 plus R. Actually, that's not necessary, right? We don't need this. No, this simplification is not necessary. Okay. So, what is VOL? It's a number which is very close to 0. VOH, number which is very close to VDD, right? So VOH minus VDD is a very, very small negative number. VOL is a very, very small positive number. So if you see this difference, it's actually a extremely small number. So for example, you could assume let, right, VOL equals VOH minus VDD or VDD minus VOH for symmetry, right? It's on either side, it's going by the same amount is what we are saying. So if that's the case, then what does that thing simplify to? VILH is 2 VOL minus plus 2R into VOL. Sorry. Right? What does this simplify to? 1 plus R comes out and you have twice VOL. So what are we saying? For a long channel inverter, this region in which the input is an indeterminate input is actually simply twice VOL. It's such a small region. It is almost like up to VDD by 2, everything is logic low. After VDD by 2, everything is logic high. Right? So that's the reason I wanted to go through this long channel inverter derivation, because it allows me to show you exactly that this is true. Clear? So that region in which, because the slope is minus infinity at Vin equal to Vout equal to Vm, that region also has to be very, very, very small for a long channel inverter. Clear? Of course, here I am assuming that VOL equal to VDD minus VOH, which is a fair thing actually, because VOH is supposed to be VDD, VOL is supposed to be ground, ideally. Okay? Any questions here? So two things. One, short channel transistor, the equations are very complex, because just think about this. Now in each of these terms, if I add a 1 plus lambda V0, just think about how you will do this differentiation and get the accurate answer. It's not possible. It's not even tractable and it's not even useful. The end of the day, I don't even get a result like this, where I can intuitively understand something from it. right? It just makes it very complex, and therefore we resort to that approximation where we extrapolate that line at V in equal to V out equal to Vm with that same slope, and then extrapolate those points as VIH and VIL, right? But for the long channel device, it is possible to derive these expressions very accurately. Clear? And if you make the assumption that VOL is equal to 0 and VOH is VDD, then you will find that this region delta VILH is basically 0. So that's also not true. So somewhere it is because VOH and VOL are not exactly VDD and ground respectively. That's when this small indeterminate region actually comes into picture. Okay, here we have made no approximations whatsoever. All expressions are accurate here. Okay.